I have the honor of introducing our plenary talk this morning, Mike Davies, who is, in addition to introducing the LiHi chip, has been kind of the organizing committee host of the meeting, so to speak. So thank you, Mike, for a great venue.
Absolutely.
So
hopefully you all get your mugs.
and for the mugs, which we all have a souvenir. So without further ado, I'll hand over to Mike Davies.
Thanks, Brad. Morning. So this is part two of a somewhat more in-depth introduction about LiHi now. In this talk, I'll talk more about the architecture. This time it'll be more of a laundry list like last time, and hopefully I'm hoping to motivate the architecture and more the basic principles and why we defined and implemented LiHi in the way we did, and then to discuss a little bit about our preliminary algorithmic and application results and software SDK, and then looking to the future. I'd like to acknowledge the entire team. This has been a long 3-year effort for many of the people on this list, working very hard, and we're very proud and happy to be where we are today. So first, just the basic kind of Intel's view on neuromorphic computing in general, and why it motivates us to get involved in this area. So I think, clearly this isn't very new to this audience, but there's an emerging demand for workloads that have, let's call it intelligent behavior. It's hard to define that very precisely, but clearly there's a need, there's a demand, and it's really not being met in the entirety by today's solutions, whether they're algorithmic or the silicon solutions. Either algorithmically, we just don't know how to do the types of learning and intelligent behavior that we desire, or we just can't really do it efficiently. And efficiently measured by the benchmark of the brain, which, as everyone knows, is 20 watts, and is just incredible in terms of what it can do, given that level of power budget and that volume, that size. So some examples of the workloads and the problems that I would identify and put on this list, listed here on this slide. And I would note that none of these are really deep learning problems. So deep learning is working amazingly well. It's a great technology, but it's not the full answer to everything we need for this coming age of intelligent computing. Supposing we are able to figure out some solutions for this, and neuromorphic computing we see as being really one of a very few solutions on a short list, there's a whole range of applications that this could enable. I won't go through them all. We obviously, we're pretty full aware of what those may be. There's great scalability. I'll point that out, though, that obviously looking at the brain, you have very, very small brains, the brains of nematode worms that are 300 neurons, all the way up to human brains of 80 billion neurons. And it's the same basic machinery, the same computational model, which spans that type of range. And it's pretty incredible. We don't see anything like that in conventional computing. So if nothing else, that gives us confidence that if we do figure this out, we'll be able to apply that to really all segments of computing, and new segments too, like neural prosthetics and pretty exciting things along those lines. So a little more specifically, how we approach this problem, how we view it anyway at Intel in our research program. Admittedly, this is all very simplified, but it may help to just kind of organize the field and the relationships between different approaches and technologies. So if you view this as 3 different domains, one is what we'll call conventional machine learning. And really that's more of an approach and a procedure, a discipline, than a particular static snapshot of techniques. But this is approaching from a very unconstrained mathematical perspective. It's not really thinking so much about what the structure and the underlying computational substrate is. It's just exploring a broad range of mathematical approaches, defining objective functions, and then quantifying how well you can learn, or you can generalize or fit to data. Then secondly, we have the topic of this workshop that most of us here are all engaged in, and that's brain-inspired computational algorithms. So that's drawing inspiration from neuroscience and trying to reverse engineer the magic that we see in the brain. Intersecting both of those is what I would call competitive computer architecture. So these are systems that we can actually build today course, this is an expanding, this too is not a static domain. As we get new technologies, this changes. But given today and the foreseeable future, there's a certain scope of system that we can build. And we want to, at Intel, in terms of this research program, we're wanting to look at that intersection between brain-inspired computational algorithms and what we can build to deliver competitive value to our eventual customers. So that's specifically this region 3 that I've illustrated, which is spiking neural networks. Talk more about spiking. This is always a controversial topic that comes up at NICE. But we do feel that this is the most promising direction for the time being. And where it gets a little interesting is that intersection with deep learning or artificial neural networks and the types of problems and the approaches of network topologies that that approach is now focused on. So that would, if we call that region 1, there's an intersection of region 2 there, which is applying spiking neural networks to deep learning types of problems. Now that's clearly possible. Spiking neural networks is really a generalization of the ANN, perceptron-style model of a neuron. But really there's a range of other behaviors and capabilities that the spiking aspect, that temporal aspect of the computation provides. That's region 3. And really we see that as the more interesting, exciting direction to take it. So we certainly want to support this region 2, but that's not necessarily how we see the best fit for this technology. This is really going after slightly different workloads and capabilities. Hopefully that region 3 is non-empty. I think we have some evidence to suggest it's non-empty, but we don't really know today the scope of what that actually is. Maybe we have to wait a couple more process generations until we can truly build systems that are economically viable. Okay, so now a little more on the philosophical end, but approaching this from an engineering perspective, this is how we're looking at building systems. So in a very simplistic way, this is obviously what's in all of our minds to some degree. Nature's figured out something incredible. We don't understand it. It's just amazing compared to anything we can build today. So let's figure it out and copy it. Now it's not that simple because we're in a very different design regime from nature. So materials are different, number of metal interconnect layers are different, we don't communicate in chemical ions, we use electrical signaling exclusively. So there's many, many differences, and that translates to pros and cons. There's trade-offs here. So mostly we're behind according to many metrics. If you look at all the chips that are being done today, we can't reach the same neural densities as you would find if you look at kind of a planar projection of the cortex, about 20 times off there. The synaptic area is still even further off in terms of, so getting to very high synaptic densities, which is really key for scaling these systems. We're maybe 400 times off there. On an energy perspective, if you look at the energy per handling a synaptic operation, we're even further off, 2,000 times off or so. That number, of course, is coming down, but we're on the silicon side. We actually have a chip developed in our program at Intel, in Intel Labs, which is under 4 picojoules. That I don't think is our focus today, is just driving that down to the lowest possible number. LiHi is not at that level. It's more on the 20 picojoule level. But clearly we're behind. We have a long way to go. And we have to work around that in other ways. So clearly we have some advantages. Our maximum firing rate is over 1 million times faster than what biology can do. Let's not say biology maybe could figure out ways to do that, but certainly with the tools it has, and it's the way that neurons have evolved there, 1 millisecond is about the maximum firing rate you would ever find, and we can easily do gigahertz circuits or faster. Synaptic error rate. So our technology is very reliable, whereas biological neurons are not reliable at all. Now, noise is beneficial in neural systems, but we have the option to not have noise, which is pretty powerful. And then there's other aspects about different assembly techniques. And one item here I would highlight is we want the capability to rapidly reprogram our systems. And in that respect, we're trying to significantly overachieve what nature does. So that has implications for the entire design and architecture of these systems, and that's oftentimes overlooked and not thought about. But that's a significant feature that in conventional computing, of course, you don't think about. But from the standpoint of copying a brain, just copying the capabilities of a human brain, if you had the ability to just download its state at any time and upload it, I mean, that would be amazing, right? And very, very difficult. Okay, so given all those differences, it's very interesting, though, that the underlying objectives and constraints are very similar. We need to minimize energy, we want fast operation, and we need things to be cheap to produce. So that means some of the same basic underlying principles will absolutely apply to the systems we build versus the systems that nature has developed through evolution. So that just leads us to the general philosophical perspective that we are trying to understand the basic principles and to apply them, not copy individual mechanisms and individual structures that we may find. It's really the principles, which unfortunately are not fully developed in all cases, maybe most cases, but at least there are some. But we also have to bear in mind these differences in terms of the tools we have available and do this in a smart way. Okay, the question of spikes. I'll try to go through this quickly, but we've already had a lot of discussion about that on Tuesday, and this slide here, I'll walk through my best ability to do PowerPoint animations to try to convey some intuition for why spikes, what we call spikes in the systems we build, are actually potentially an efficient way to do computation. So biologically, of course, spike is a pulse of voltage. It's an event, it's an action potential. It's in time, it's encoding information, and it just distributes through the network of axons and dendrites in a rather slow way, but with very, very high fan out. That's a digital process. It's an asynchronous digital process. The state is normally 0, where there's relatively low energy power, and then there's an energetic event, which is the spike, which is a 1 that propagates along. So if you look at how we would implement that in digital circuitry, it's on the surface of it, it looks incredibly inefficient. We have to represent these spikes in multiple bits, 16, 32 bits. And we have to route these spikes in some way because, again, we want reprogrammability. We don't want to just draw one wire and that's the wire forever. We can't have adaptive systems, hardware at this stage. So we're transferring these packets now. These can still be asynchronous and event-driven in the way that an action potential is, but it is definitely many bits that are moving along, and they have to go through these crossbar structures, which is a lot of circuitry. So it looks very, very inefficient. On the other hand, consider that it is certainly possible today to put those 16 wires there in a 1 micron dimension, which is actually the average diameter of a myelinated axon. So in terms of the scales, they're actually not that far off. And admittedly, the crossbar itself has a lot of circuitry that's much bigger than a 1 micron dimension. But consider we're running at 1 million times faster. That time multiplexing capability of being able to pipeline transmission using the same interconnect reduces the area overhead by that factor. So effectively, the routing interconnect is 1 million times smaller than it may appear. So bear that in mind. That really leads us to believe that the interconnect can be a very straightforward meshed NOC, and for the time being, that is absolutely sufficient because we have this tremendous overspeed and it's amazingly reconfigurable. Now then, stepping back up to the macroscopic scale, we have, what does this look like when you have this mesh of cores? And now you have this sparse activation of these messages. And what's important in this case, in this computational model, is the fact that 2 of these cores, 2 of these neurons, or many subsets of these neurons are communicating. And there's a tremendous amount of encoding capacity in that. If you think about the possible sets of communicating neurons, and you consider the temporal dimension, so there's coincidence detection, and then that computational element, which gives you combinatorial options for representation and, of data. It's ample to do any computation you may require. Compare that to a traditional memory architecture, or a traditional CPU or chip architecture, where you have a tier, hierarchy of memories, you have computational CPU elements, and data is always flowing in a very dense manner through these memory structures, through the pipelines, and back. and is just always circulating in this kind of highly synchronized, continuous manner, is just a much greater level of communication. Sure, it's very general purpose. You can do many, many different computations that you'll never be able to do in the neuromorphic fabric, but on the surface of it, it's not a clear call which is the efficient and which is the inefficient approach. Looking at it a little more abstractly, what is really, and here you can just stop thinking about neurons at all. And if you just think about the digital pipeline of what these neuromorphic systems that we're building look like, it's really a series of table lookups. I mean, that's mathematically, it's that. It's a, like a LUT you might have in an FPGA, but scaled really large. Or these tables are sometimes very large, 32K entries. And a table lookup is a very powerful computational structure. It's highly nonlinear. You take an input, you map it in some arbitrary way to an output. You have many, many different options for programming that function. And then there again is the temporal aspect. So there's, all of these are typically self-modifying structures. So you have this sparse propagation of these packetized spikes, and that's doing computation simply through the transformation of those packets. And the computational aspect, everybody focuses on the synaptic operations. That's just one very, very small part of this pipeline, and arguably not the most important part by far. It's just the movement of data and the synchronization of that data in time across these different computational elements. Again, if you compare that to traditional computation, well, you have typically one big table lookup, which is the memory, and you're reading everything out of that. You're going through some complex decoding structure, which gives you the tremendous generality that you can encode all kinds of different sorts of operations. But is it efficient if you want to do neural type of computational workloads? Not at all clear. There's a lot of activity, there's a lot of overhead if you're taking that kind of an approach. So anyway, that's just the intuition. That's one perspective on why we're pursuing spike-based computation. But you don't even have to buy any of that, because we do have one compelling quantitative example. This is lasso sparse coding that we've analyzed, and we've rigorously benchmarked against the best conventional solutions for this problem. And we found that the neuromorphic implementation gives orders of magnitude improvement here. So sparse coding, lasso, it's not necessarily learning ImageNet. It's not an amazingly computational problem yet. It's not intelligence, but certainly it is a very well-defined, difficult, non-trivial mathematical optimization problem, and it's very intriguing that it's solved so efficiently with spikes. And really, computationally, this is a primitive type of computation you find throughout the brain. There's many structures that do this kind of an operation. So it's in some ways sort of fundamental. It also exposes a few lessons, I think, about how to get efficiency out of neuromorphic systems and neural computation. So the lasso network, specifically this is when formulated in terms of what's called the locally competitive algorithm. This was first developed by Chris Rosell. We're not the first to recognize that there is an efficient spike implementation, or even the first to build hardware to implement it efficiently. But we've studied this in very great detail. So what you have is a balance of excitation and inhibition in the system. So you have an input that's being distributed among many different feature neurons, and each of those feature neurons encodes something in an over-complete set of dictionary features, trying to represent that input. But they're competing to represent it with as sparse a representation as possible. Of course, that already suggests there's maybe some energy advantages with that, because sparse means low activity, and that's exactly what this problem is solving, is trying to find the minimal representation while also minimizing the error of that representation. So that algorithm, surprisingly, I'm not even going to talk about neuromorphic implementation yet, but when you take the spiking form of that algorithm, this chart here shows the time to solve a particular sparse coding problem on a Xeon. So both the spiking implementation and the best conventional solvers, which are Fista and Lars, solvers such as that. And the spiking implementation actually outperforms these state-of-the-art conventional solvers. Now there's a caveat. They outperform only to a certain degree of precision. And so that's definitely one overriding lesson, is that neural computation, spike-based computation, won't ever take you to 64-bit floating point solutions. We can get within 1% of the optimal solution with this spike-based approach. We can get to that 1% solution much faster than the conventional approach. This is purely on a sequential processor. Now, of course, the LCA, the network, this type of a network, once you do have an algorithm that is formulated in terms of this granular neural representation where all the communication and computation is happening through local interactions, now you know you have a perfectly parallelizable algorithm, and you'll get strong scaling into a granular neuromorphic implementation. So also to maybe, I've got a little video of this algorithm in action. So this is just the typical spike raster plot on the right here, you can see, and this is the objective now in a predecessor of LiHi. With that parallelism, you're getting a tremendous speed up now in just dropping that objective function down to the 1% solution. But so it's tremendously fast. The other very intriguing thing is to look at the pattern of spikes. And there's this extremely brief period where there's this very intense period of computation, and then it settles into the solution. At that point, what you read out is the fixed point of this dynamic system, which corresponds to static rates. So when you read it out, you have a rate code. But the computation is really at the fine granularity. It's a very temporally significant sort of computation that's going on. The most strongly activated neuron is the one that's firing first, and then that's inhibiting all its competitive features that are similar to it. It spiked first, so therefore it suppresses all the other ones that are just not quite as good. And that's what's happening in this very brief, intense period of activity, and that's where the efficiency is really coming from. Okay, so building on from that, what does that give us? We've already, that's a compelling example, and it's not particularly specific to a particular computation. You can see similarities to all kinds of other neural networks, EI networks, LSMs, various different familiar models of neural computation, which tells us we're onto something perhaps. So we can now take what we talked about earlier in terms of efficient mesh-based neuromorphic fabrics, accept that as a reasonable architectural approach for building these systems. And then we can just take the integrate and fire neuron model with a exponential synaptic response. And we have a preliminary neuromorphic architecture here. What is certainly important is that we support the fan-outs that are needed. That means we have these additional table lookups to implement the routing to get to the feature neurons that we need to. This representation I'm showing here of a neuron is maybe unfamiliar to some, but from anybody from an electrical engineering signal processing background, this is basically what this neuron is. It's a very straightforward filtering process. So that's it. That's what this system is, baseline. Now, of course, there's various enhancements. We think about different algorithmic directions, and we keep adding more features to this, but this is really where we start. There's one significant problem, though. And that's how do we scale this up? So LCA, as I showed that network, is an all-to-all connectivity problem. So each of those feature neurons has to talk to every other feature neuron. So there's an n-squared connectivity problem. That just doesn't scale. You can maybe go to 1,000 features, but you get to 10,000, you're suddenly exhausting the ability to represent that many weights on a single chip. So we need to think about ways to sparsify this connectivity. In the case of LCA, there's a very powerful way to do that, inspired from convolutional neural networks. And of course, this is inspired from the brain itself. If you look at the convolutional receptive field structure of the visual cortex, that's where this all came from. And it's recognizing that there's redundancy in the network. So a lot of those weights that are involved in that computation are repeated across the entire visual field. So that's a good trick that we can take advantage of, use the fact that we're time multiplexing and we can repeatedly access the same weight state to get us efficiency in that neural structure. But also what this provides is once we have that, then we don't have to solve an image, let's say, as one big problem. We can approach that in the more neural convolutional way where you have different circuits, different feature neurons that are applying to different patches of this image. So what we've done in extending this idea, in the convolutional world, this is pretty straightforward because you have a feed-forward network and you're just applying a simple convolution across all of those different patches. LCA is not that simple, and recurrent neural networks in general are not that simple. If you thought about EI networks as a processing unit here, or something more general, there's recurrent connections. And so it's not just a simple matter of taking a single convolution of your input. You need lateral inhibition, or just lateral connections in general to other feature neurons. So what that drove us to do is generalize that and create a notion. I've kind of shown it here is for the LCA case. You now have these kind of population to population or feature neuron to feature neuron recurrent connections, which have to be also encapsulated and modularized so that they can apply it in a hierarchical way. Generalizing that completely, what the model that the architecture we settled on has is this population-based connectivity model. So it truly is a hierarchical approach where you can think in terms of your network as being neuron types, populations, and you specify a template connectivity between those populations of neurons, and which then you can bind down to any particular set of population instances. This is all within one core, with then population spikes connecting between cores. So that can provide tremendous compression in the connectivity state that's needed to represent some of these networks. And I would also point out that this is intriguing from a computational perspective, because convolutional neural networks is a feed-forward computation. So it's pretty straightforward what's happening, and the computational, you're repeating a dot product and you're factoring out some of those weights. In this case, you're creating an interacted coupled dynamic system by having these lateral connections. So this leads to much more powerful dynamics and computation by being able to create these more generalized hierarchical networks. So with that, we can now scale up to large problems, and then this is the quantitative result that we get when we go and attack an actual image like the one I showed using this convolutional approach. We get almost 50 times speed up compared to a conventional CPU. By the way, we're comparing this in terms of an atom just to normalize and control for silicon area. So as you know, in engineering, there's always different trade-offs you can make, and going to larger and larger CPUs with more computational horsepower and parallelism may allow for faster computation, but it costs something. So we have to, this is a case of controlling for area as well as process, voltage, every parameter you might need to keep apples to apples. So we're 48 times faster, 118 times lower energy, and that leads to a total of over 5,000 times improvement in energy delay product, which is a common metric of computational efficiency. And another intriguing aspect of this is, if you look at different size of problems, there's this clear trend to, as you scale these networks up, you're taking more and more advantage of the parallelism and the goodness of this neuromorphic architecture of what it's providing. So we intend to keep studying this. This is a somewhat old result. We're right now still working on mapping this to LiHi, where we'll have a lot more flexibility for looking at different problems and different scales of problems. But clearly we expect, and we've seen this in other problems we've looked at, there's this clear trend where if you find the right algorithm and there's a good match to the neuromorphic architecture, then bigger problems are better. Okay, so I presented this slide on Tuesday, but just to kind of give another reminder of what the full feature set that's in the chip. And I wouldn't say in every single case here we've motivated the feature set in the same principled way that I've just walked through, but almost every feature here we did do some level of modeling and tried to really understand if that feature really has a computational place, whether the precisions we're using are adequate, whether there is really some algorithmic tangible need for all of these features. And I think the answer in almost every case is absolutely yes, and it's just a matter of time to go and unlock the potential and start using these things and figuring out how to solve hard problems. Of course, there's the learning aspect too, which I'll talk again more about. This is the most novel aspect of what's in LiHi, so I'll come back to that. To summarize the non-learning behavior, though, this pipeline diagram might be helpful. I don't want to go through a bit-by-bit description of what's going on in the chip, but I think just that this is like the first next level down into the core design and what's going on. What you have are two decoupled asynchronous processes operating in parallel. One is handling the reception of spikes that are arriving at the core. This is, as I've said earlier in the last talk, this is a digital time multiplex pipelined core. So that means that what I've shown here in this diagram is kind of the unrolling of time into space. That's why there's all these different lines, these channels across, which you could think of as different neuron pathways or computational pathways. That's all compressed into one time multiplex system. But what happens is a spike arrives, it gets looked up through some series of routing tables. That's a very complicated operation, but we can just encapsulate that. So it's distributing the spike among all the synapses that it's connected to. And all the synapses has a delay associated with it, which means it then destines that spike operation for some future point in time. We need at least 2 of these time buckets because of the barrier synchronization operation I discussed last time. So any spikes that are being sent in the system for the current time step, they are getting generated on that time step. They must be serviced on the next time step. So to preserve coherence in the overall computation, spikes have to be handled into some stored temporarily in some next time state variable. That's what this circular buffer is implementing. Once you have that, you might as well support more than one delay. And so that gives us temporal coding synaptic delays very efficiently. Now, in concurrent to that, you have the dendrite process, as we call it, which is really the neuron models. And that's reading out the current time state accumulated synaptic activation, and it's applying the neuron model, the Cuba, leaky integrate and fire neuron model, reading parameters, updating neuron state. If there's a spike, if it's activated the threshold, then it activates the downstream output routing table, and the spikes are then distributed into, injected into the mesh and delivered where they need to go. Okay, so coming back to learning, synaptic plasticity, one of the fundamental concepts here is that of a local learning rule. So this is why backpropagation just doesn't work in a neuromorphic fabric. Every weight change in a synapse has to be happening based on locally available information. What is locally available information? Well, in this diagram, here's a very simplified network. You have a weight from X to Y. The only thing that's locally available is the presynaptic state X and the postsynaptic state Y. That's it. So if you have some supervision signal, calculating some error, that error is not available. In a proper neuromorphic implementation, you have to find some way to route that error to the postsynaptic neuron or the presynaptic side. You have to get it to the place where you want to make those changes. And that's really the hard part. There's a lot of good work trying to map backpropagation in some transformed manner into this kind of an architecture where these credit assignment can be done and distributed in a local way. That's the problem. You just don't have an ability to just propagate backwards derivatives, successive layers, and update weights incrementally like that based on this global signaling. Now that said, we do have some mechanism to implement some modest scoped global computation, and that's through what we call reward spikes. This is mainly motivated from the perspective of reinforcement learning, biologically inspired. This is a neuromodulatory, maybe a dopamine kind of signal, something along those lines. But what it is a special spike type which has some distribution to a scoped set of axon fanouts. So that allows you to then provide some generalized feedback in terms of this was a good decision or this was a bad decision, and then apply weight changes in response to that type of a feedback. But it's still signaled through spikes in the sense of an event-driven packetized message through the mesh, and it preserves the basic energy efficiency and parallelism that we're looking for. So learning rules in general, the way we feel that they should be developed is in this pretty rigorous kind of top-down mathematical way, so that you know what they're doing. There's a lot of exploration of STDP, simple pairwise STDP, playing around with this in networks, and maybe that will lead to something. There's certainly intriguing results that have been shown, but people have been playing with this simple pairwise STDP for a very long time. Hasn't led to any kind of compelling results or competitive accuracy. So On the other hand, there's been some more recent work which is taking a more principled approach of saying, okay, we have some statistical objective that we want to achieve. We want to maximize the representation of this data set. And given that, can we derive local learning rules given the dynamics of the neurons that we're dealing with? And that is leading to really great, rich space of new learning rules to start thinking about. And coming from the computational neuroscience community, these are local, so that they are compatible with a neuromorphic implementation. We also need plasticity on various timescales. So reinforcement learning is the most obvious aspect of that, but that's a much delayed, this reward or punishment signal comes a long time after a particular action. There has to be some state that gets preserved to the point where that reinforcement signal comes back. It just means there needs to be a variety of timescales that are supported by the system. And if you look at some of these learning rules that are being developed, even something like a simple inhibitory STDP pairwise learning rule, you have an interesting shape to this curve in terms of the temporal dimension to that. And really there's multiple timescales involved in shaping the weight changes over time. So that's important that learning rules support that and that the hardware supports that. So that's what led us to the LiHi learning architecture, which what we call a trace-based programmable learning approach. Traces meaning a shorthand for just filtered spike trains. So anyone from the computational neuroscience side, totally familiar with these, and these are pretty fundamental. And any of these neuroscience-inspired learning rules are all formulated in this sense. This is really corresponding to what's happening in the biology, where you have exponentially decaying receptor ions being bound and then decaying away. So there's sound biological reason why you have this kind of a filtering process, but it's also very, very natural from a signal processing, a conventional approach to implement kind of decaying state over time that has a time scale to it. That's just a standard first order filter, and that's exactly what we're implementing. Now you need these different timescales, as I mentioned. So very short timescales gives you sensitivity to correlation in time over very short timescales. That's standard pairwise STDP. You can also have long time constants, in which case you start accumulating information from spike to spike, and you get some measure of a long-term activation, which is putting you in the rate regime. So the LiHi learning architecture can combine both of these. We actually have multiple state variables per synapse so that you can simultaneously have short time scale state and long time scale state. So here are some examples of what the LiHi architecture supports. So pairwise STDP, of course, but also quickly you can get to more advanced rules like triplet STDP. You can have homeostatic decay terms in there. You can assign learning rules to delay, so you can think about kind of delay, directly temporally coded kind of delay-based learning rules. Building even beyond that, you can define learning rules that uses this kind of temporary scratch variable we've called a tag, inspired from synaptic tags and eligibility traces. And so you can have these kind of distal reward types of learning rules where you provisionally capture a weight change that you may make, and based on some reward signal later, you apply it or not. And so you need two state variables, and that's supported. You see the green term here is that reward spike. And you can build up to very, very complicated rules like this last one, which has some kind of inertial term, which might be helpful for not forgetting too quickly. So just only when you have enough statistical evidence would you actually start moving your long-term weight value. Okay, so moving on to just some of the other kind of novel algorithms that we've looked at with LiHi. One is a class called we're calling spatiotemporal attractors. So this is generalizing from Hopfield type of spatial attractors. So this is really inspired out of the olfactory bulb and gamma cycle type of sort of iterative computations where what's happening is there's an attraction. It appears, I've got a little animation of this, to a particular spatiotemporal spike firing pattern. And that's happening through iterative gamma cycles, and it's very well understood. In fact, you'll hear Tom Cleland talk about that shortly. I think he's studied this in great detail, and that's the work that's inspired some of this approach. This is still work in progress, but certainly it's an intriguing direction to go to get more representational capacity, more generalized patterns with fewer neurons. Another is looking at stochastic spiking neural networks and solving problems like constraint satisfaction or Markov chain Monte Carlo. This is inspired from Wolfgang Maas's work with looking at how you can start viewing these spiking neural systems as converging to a particular statistical distribution of activity. And it's actually the statistical emergent dynamic distribution there, which is doing computation and not the firing rate of any particular neuron. It's really the collective macro state of the network. And then finally, there's graph search is another one we've done, which is inspired from the way that these kind of SynFire sorts of waves propagate through the hippocampus. And through a really interesting mechanism, you can explore all paths from a particular destination to all sources. And then from whatever source position you may be, you can then follow the effects of STDP in encoding what the shortest gradient path is to the destination. And that actually has better scaling characteristics compared to conventional Dijkstra's. Okay, so I won't go into detail on this, running short on time, but this is kind of our Hello World application. You can look at it and you can see all this detail in the demo room. We actually have this set up and live and running with real objects and very, very primitive. I mean, this is literally 20 neurons. So if anything, it's just showing the potential for 20 neurons in a chip like this to learn dynamically, at least in a pretty quick time frame. 4 seconds to get to a usable level of accuracy. It takes longer than that to get to near 100% accuracy, but there's some skepticism that spiking neurons at all can get to very high accuracy levels and high levels of precision. Well, here you can get to effectively 100% accuracy. You can do that in very low energy too. So a bit about the software. If we pop up to kind of the 10,000-foot view, this is really the vision of the whole framework and how this unifies with really getting pretty far away from neural computation, but more just parallel systems and event-driven asynchronous communication through sequential processes in general. So this is really our vision for the highest level system architecture, where you have a collection of hierarchically specified modules. Some of those decompose down into conventionally specified sequential processes. You code them, very understandable what they do. In other cases, you decompose them down into much less understandable computational elements, such as spiking neural network systems. In each case, you reach down to some atomic level in some sense, where it's the lowest level of abstraction of computation. Of course, that would be a spiking neuron in the spiking domain. You might also have interleaved or supporting parallel sequential processes we're calling SNPs, for lack of a better term. But these are basically conventional small programs that are doing things like format encoding, decoding, or assisting in implementing more general neural computational processes that happen on lower timescales. Best to just code that up in a standard processors. Maybe that's modeling astrocytes like we heard about yesterday or something like that. And these get distributed into the system. It gives you some very parallel granular implementation, has a mixture of conventional processes and neural processes. It's all communicating through event-driven asynchronous communication. The challenge is in knowing what the system will do. And so for that, what we hope we can unify in this framework is a behavioral description of what these more complicated spiking domains are doing. There may be multiple different behavioral descriptions of that, but I think that's key. Representing that into some eventual framework is key for being able to reason and thinking about how to assemble these systems and solve larger problems. That behavioral description is not the implementation, but it's more just the model that represents the behavior, the emergent behavior. Of course, there has to be a mapping of that into the physical layer, and there that may not be hierarchy preserving. Certainly, we don't have discrete neuron implementations, so those neurons get reshuffled and implemented in a different core-based digital pipeline architecture, but there's an abstraction, and it's useful to think in terms of that abstraction layer. Some of those processes may even be implemented into an FPGA technology, and our design methodology that we used for LiHi supports exactly that. You can specify sequential programs which then get compiled down into hardware that could be mapped to an FPGA. The system architecture today looks something like this, where we have kind of a three-tiered approach. You have LiHi, which has embedded simple von Neumann x86 processors. I mentioned that on Tuesday, 3 of those. Next level up, outside of the LiHi processor, we have an ARIA 10 FPGA, which itself has an ARM CPU in it. We call that the host. You can pop out yet another level, and then you have the ultimate laptop or Xeon that you're sitting and kind of compiling the networks and the conventional code of doing the mapping into the structure of the system. We call that the superhost. The ARIA 10 FPGA we're using to interface to sensors and actuators and those sorts of things. Not too much yet. We do have a robot arm that's being controlled by Chris Elias-Smith, and he'll talk about shortly. But not too much that we've connected LiHi to yet in the real world. Of course, the LiHi chip is scalable to multi-chip. The systems we've built today have 4 chips on them. We're definitely planning on expanding that out. We're not trying to build really big networks, really just trying to provide enough resources for multiple users to access and use at the same time. Okay, so the software development kit, this is just a complicated diagram, but shows the basic how there's a layered approach to this. There's some user code that has to be mapped all the way down to the lowest level. We're still building this all out, by the way, so this is very much work in progress, but this is kind of the near term where we're going here. There's kind of successive higher levels of abstraction that you can write these programs at. We're building it from the bottom up, so the top is where you want to be programming. Today, you're kind of at a lower level than you'd like. We definitely plan to interface to standard frameworks as well, so Nango being one that's probably coming in relatively soon, but others too. We also have a functional simulator where all of this is running at the Xeon software layer. But there's an open question of what is that right framework for the very highest layer. It's not TensorFlow. There's no tensors in this system, right? It's just the wrong abstraction unit. The nodes that are in a TensorFlow framework, we can't support but a tiny fraction of those. And it's just the wrong framework to be thinking about this kind of an event-driven spiking neural network system. So it's an unclear, open problem of what the right framework is at the top level. This is a quick kind of outlook on the systems that we're building. Today we just have effectively a bring-up platform. We have several of these. We've put it into a kind of a hosted remote access form. But it's at very, very small numbers, and we have extremely limited bandwidth to be able to support many people using it. We're trying to build that out over time. So soon we'll have what we're calling the Nohuku, 8 LiHis per board. We'll also put those in our remote access cloud-based service. Eventually we'll be able to give those systems out more in kind of the late Q2 timeframe. Then we're going to build up a system that has many CPUs in it so that, again, to just support more users mainly, not to necessarily scale up. Finally, I'd like to just say something about a community that we'd like to launch. We're calling the Intel Neuromorphic Research Community. We don't mean to exclude anybody by calling it Intel necessarily, but clearly we have an agenda in what we'd like to explore here, and that's to use LiHi itself. So that's really what defines the focus in this community. There's a number of different research vectors that you can think of it in those terms, different categories of problems that we'd like to tackle. Everything from the basic theoretical ideas. There's no good understanding of a complexity framework for neural computation and the types of when you ground it into a particular hardware architecture. You can make some very concrete development there, but very little has been done. The algorithms being really the main focus of finding how to solve real problems, sensing, control, applications. So we have various goals for this. We want to share code. We want to share results within this community, share algorithms. We'll create an open source code repository where all of these things can be shared among community members. And ultimately, this is going to drive improvement in our silicon into future generations. So we'll give you remote access. We'll loan out a LiHi silicon and systems in some cases where you really need that. There's also an opportunity for a limited amount of funding. This is kind of grad school, kind of a student level of funding for particular research groups. There'll be a process to apply for that, RFP coming out later this month. this gives some kind of sketch of the time frame, just not putting any numbers on here because we just don't even know what we're going to be able to support in terms of number of partners. But there's a tiered approach here. We are going to be at Telluride. There'll be LiHi systems at Telluride this summer, so certainly encourage you to go there. That would give you immediate kind of hands-on access to the chip. Otherwise, we'll be doing a series of workshops, again, successfully broadening it to a more and more larger base of users. Ultimately, building out, the goal would be to get to a point where people are coming without any kind of prior background in spiking neural networks, don't even want to think about neural networks or spiking. They just have hard problems. They want the right tools and the silicon solution to solve that. So, thank you.
Time for a couple questions.
Hi, thank you for the presentation. The onboard CPUs, what kind of information about the state of the neuromorphic cores do they have access to?
They have access to just about everything because the management operations read-write messages are in-band through the mesh. So it's a unified address space, and we've exposed all architecturally significant state to that memory space. So you wouldn't want to dump all the state all the time. You know, obviously, it'd be tremendously inefficient, but it's all available.
Awesome, thank you.
So I have a quick question. So what is the sort of synaptic density limitation? So obviously, your synapses can be a varying level of complexity. But if I have a reasonably simple synapse, I just want to have a lot of them. Like, am I able to kind of tune the number of synapses relative to the density of the synapse or complexity?
Absolutely. So that's we've put a huge amount of flexibility into that synaptic mapping function, possibly too much. But effectively, what you can do is you can have single-bit synapses, single weights, if you want as few as that, and densely pack it in as a bit vector effectively into that memory. So you have 128 kilobytes of synaptic memory. You can divide that up however you like. You can have up to 9-bit weights. You can have 3-tuple synapses that have weights and tags and delays, or you can shrink that all the way down to the minimal case of a single bit per synapse.
Yeah. Last question.
Yeah, Mike, nice talk. Coming back to one of your first slides where you had the energy metrics, you were showing something like 4 picojoules per synaptic event if you do it on conventional hardware, right? I would kind of dispute that. If you look at ISSCC, like a 4-bit machine learning system, that's doing like 15, 20 teraops per watt. If you do the math, that's about 100 femtojoule per multiply and accumulate, so per synaptic event.
It's a
so you
different
actually
synaptic
factor
event.
40 better than what you've shown.
Right, but that's a different type of a synaptic event, right? This is including, so granted, there is absolutely some overhead for a spiking implementation. There's temporal state that has to be decayed and updated over time. This is a fully sort of average number. So, you know, that's focusing on a synaptic event, but it's including all energy in the system, including memory lookups, routing of these spikes. There's an overhead. If you just compare that literally to a MAC operation, you know, in a conventional deep learning accelerator, of course there's a difference. There's overhead to implement the temporal aspect of what's going on. That's why in those scaling charts, you need to get to a certain scale of a problem before the parallelism, the benefits of the temporal element of the spiking model provide an advantage. Because below some level, yes, if your computation is beautifully mapping to a local, continuously formulated, graded ANN type of a problem, you'll be better off solving it in that type of an architecture. But it's really about the scaling. How do you scale? How do you get to a sparse level of communication so you're not continuously moving dense vectors and tensors of data around the system continuously?
Yep. I kind of agree with you, but it's still, those energy metrics, they are for big systems, and it's basically wall plug power divided by the operation. So they take the entire overhead also into account.
Oh, sure they do, but it's a question of what problem are you now solving, right? You know, you have to bump up to the actual workload problem level as opposed to fixating on, you know, the particular number at that level, because you're doing many more of those computations potentially to solve, you know, the problem you want to solve. That's the key, is the number of those operations in that case, in that particular comparison.
Okay, yeah.
So.
Thanks.
Sure.
All right, let's thank Mike again.